be Judicious API documentation for novices. Luca, Chiodini, Simone, Piatti, and Matthias, Hauswirth. Take it away.
Thank you. So to bootstrap this talk, I need a little bit your help. So I'm going to do the following. I'm going to show you very small fragments of Python and what they output on the console. And I would like you to give me an explanation, a very short explanation of why that is the case. I'm going to start with the first one. So here is the first program. This program uses the print function with a string to output splash. Fair enough. Second program, who wants to give it a try? Right? But the point here is to explain why that is the output. What is the program doing? Right, so it's taking 24, which is a number. It's different from before that it was a string, and it's producing a string representation of it. And actually, we could pass in other kinds of values, and it would also produce their string representation. Fair. Third example. What's going on here?
Yeah, so you put a new line at the end of each.
Right, so we're calling print multiple times, and then this is each value is printed on each separate line. Good. This is probably not the output that we would want. Let's see a variation of this. What's going on here? Sure?
Yes, there is a parameter called n that has the default value, and you can change the value explicitly by telling to the space or whatever.
Right, so we're telling it an empty string in this case, that we don't get any end line terminator, and then we get our SPLASH-E24. Correct. Yet another variation. What's going on here?
It seems to be separating with spaces as opposed to new lines.
Right, so it's separating it with spaces. And as the last program, this one, for which we recover our SPLASH-E24.
You kind of the same thing like with the new lines. We replace the separation default value, which is a space with like an empty string.
Right, empty string, perfect. So what did we learn from this small example? Well, the first thing is that the print function is actually not entirely trivial. I mean, the first one was an hello world example, but then we went a little bit into the subtleties of it. And the second one is that you, being experienced teachers, went for gradual explanations. You didn't just dump all the complexity of the print functions with the optional parameters at the first time, but you brought it up when it was needed. And so the idea here is, can we do the same with documentation? Now, if you tell students where to look for an API documentation, well, you may tell them, look, there is a place, let's assume that this is in Python, there is a place that is the authoritative reference. It's the python.org, there is a documentation for the standard library. The problem is that the documentation of the print function looks exactly like this, which is not exactly approachable for a novice. It's great because it's complete, it's the authoritative reference, but this is what I dubbed professional documentation. So it's documentation meant for professionals. That kind of documentation is also readily available in IDEs. Here is VS Code. If you type in this code and then you use your cursor to over print, you get this version, which is somewhat similar to what we saw before. And then sometimes as teachers, we feel that this is kind of not ready for our intro to programming course. And so we resort to creating what I'm calling here forms of ad hoc documentation, some kind of special documentation that we write purposefully for our students. Here is an example of a piece of documentation meant to explain different functions available for a turtle graphics library in Python. There is an example of calling a function a little bit weird because then it's not clear there the parameter, there is a description, there is a synonym, an abbreviation, another function that does the same. And then in the last row, there is something even weirder because there the parameter is put within quotes. I assume to mean that that's supposed to be passed as a string, although it doesn't necessarily need to be a string literal. So whenever we have this form of ad hoc documentation, we are running into the risk of having inconsistencies, and we don't have the gradualness that we were aiming for anyway. So the goal here is really to have gradual explanations for this documentation, and possibly also to support learning. What if documentation is not just something boring that students have to read, but it can also aid their learning while they're learning to program. So how do we do this? So the goal is to have documentation for novices, but we as a community have resources that we have already thought about. One is programming languages. I know that there are people in the room very fond of the idea of using gradual programming languages, and so we can bring the same to documentation. And we also know something from research in computer science and math education. Now let me start exactly from this. If you look at a textbook, let's say middle school math textbook, and look at how they introduce the idea of a function, you may find something like this. Some kind of machine here that has a rule and then has some form of input and some form of output, and it's kind of this machine that transforms what comes in and produces something that goes out. And a similar notion has been used already a long time ago to introduce functions in programming. This is Brian Harvey, 1997, introducing functions in Logo, and it's using this idea of tanks, so things that, or pipes if you prefer, with things that flow in from above and things that flow out from below. And then you can imagine composing your program like this. So this is quite interesting because we can get a diagrammatic representation for functions, and we can start introducing the idea of a function there. So this is an example of the log function from the math library in Python. And what we are doing in our system is that we can actually provide multiple representations for this function. So here is the graphical one with the diagram, but we also have the signature. And it's known from the learning sciences that having multiple representations can help learning if you manage to convey to the students what is the relationship between the items in the various representations. So here is an example of the whole complete description for the log function. And the key here to aid exactly in understanding what is what and how is that X there in the parameter in the signature related to the incoming arrow of the diagram and related to the description of the parameter. If you hover over one of these items with the mouse, then the system actually highlights the corresponding elements. And where is gradualness in here? Well, there are some buttons there to the top right. You can use one, for example, to show the types. We know that in many contexts, Python is introduced without type annotations, but the language now supports type annotations as well. And so we can gradually introduce them when the teacher feels that they are ready to do this. And the other button controls whether we want to show optional parameters. For example, this log function doesn't just have the number, but it also has the base of the logarithm, and this is represented in the diagram as this dashed arrow. Now, this is the basic idea of the gradual approach. We think that the approach can actually aid with some known difficulties from CSED research. Let's review some of them. For example, this idea of bringing in from math the concept of functions works well for pure functions, but doesn't work anymore when we have functions with side effects. And so the system highlights with a special annotation, both in the diagrammatic representation and in the general description, when a function has a side effect and breaks this mental model of the students as functions in computer science, as functions in mathematics. Then another documented misconception is when students don't really understand the concept of parameterless functions and maybe even the syntax of calling them, that we need to kind of put parentheses even where there is no argument, and how is that different from a constant. And here we're helping this with two different representations. Here is an example of a parameterless function. It's the random function from the random library. And this is shown as with no incoming arrow, but it's still a function. It's still this red rounded rectangle. And here is instead how we are representing constants in the same system. constants are represented as these blue squares, and this should help reduce the confusion. Again, we know that some students really don't understand where some functions come from, these built-in functions that they are not importing, but they seem to be readily available. So how the system normally works is students type in their imports, and then a documentation bar appears at the top with names that have been imported, and then students can click on one of them to open this popover, which shows the documentation I was presenting before. But what's interesting is that the system actually parses the Python code and recognizes when built-in functions are being called, and of course students are not going to import them, and it adds these built-in functions as well to the documentation bar. And so, for example, this is a very common pattern of Python code. I think it has been shown something very, very similar to this also in earlier presentations today. Students can click on the input, for example, and learn about this function that may or may not be called with a specific prompt. Fourth, and second to last difficulty, variadic functions. So we showed at the beginning that we have this print function, and this is how it's normally introduced, or you just pass in a value and the value gets printed on the standard output. But this is the reality of the print function. So it has a bunch of optional parameters like the separator and the terminator for the end line. But it also is variadic, meaning that that value parameter there can actually take in multiple arguments, and they will be all printed space separated. And so we are conveying this with the standard notation in Python with the star and with the 3 arrows in the diagram. Lastly, we have this idea of having students defining their own functions, and it's very tricky to have them understand that their functions are no different than the functions that have been implemented in the standard library. Someone implemented those functions in the standard library, and there is no magic going on under the hood. So students can just define their own functions normally. This is without any particular annotation, and the system already picks up these functions. So you see that there is this greet item in the documentation bar with a slightly different icon, which means that the function comes from their own code, and they already get the documentation in a form that is very close to what was shown before. If they do something better, and they add, for example, type annotations, which are optional in Python, and they provide the documentation in the form of a docstring using the classic Python convention, actually the system generates a fully fledged documentation with the annotation and the description. So you can try it out. We have a publicly available platform. If you want to use, or if you're using or teaching Python, you can use this as a documentation. If you want to check out and integrate it with other platforms, the system is also open source, so you can go check it out on GitHub. There are some questions on what could come next. A first one that comes to mind is providing examples. Now there I'm kind of reproducing what would normally be found in the standard Python documentation, but it's sometimes easier to understand functions from their behavioral perspective. So showing like pairs of arguments being passed in and return values of the function may or may not be easier than reading a long text description, which we know is hard for students. And of course, all the claims I made, which are informed from research, will need to be tested with the user. So a big empirical evaluation is definitely needed here. I just wanted to comment that we actually use this with real students. We have this tried out in middle schools and high schools. We talked a lot today about doing stuff with pen and pencil or pen and paper, or doing unplugged activities. So this is like students playing around with these cards on tables and then composing their programs. And you see like they have like their API reference somewhere there, which is like just like this page with all the constants and the functions that are laid on the table. Thank you for listening.
Thank you for the talk. Very interesting idea. I was wondering, how did you choose the graphical representation you use, especially if you seem to use it with a high schooler or primary schooler? Because it seems to me that you could have used something closer to block-based programming, and maybe it would have made sense. Did you think about that? And if yes, why didn't you use it?
So part of the inspiration for the notation is exactly hard-based notation that I've shown before. So it's this idea of showing these functions as black boxes that are normally done in math textbooks and also in computer science, say logo. So that's one reason. For the other part, in the block-based programming, we actually really wanted students to work offline and without the computer. That removes all sorts of burdens of the syntax. Say we use this in middle school. There is some resistance, of course, of not trying immediately on the computer, because that's what everybody wants to do in a programming course. But we think it's rather cool to have them work on this, and it actually helps them think about programming in a way that is different than normally is done. So that's the inspiration.
Okay, thank you very much. Cool idea. I was wondering, these documentations you've created, are those created manually, or can they also be generated in any way?
So they are currently created manually for the Python standard library, because those are also created manually for the ones that you see. Normally, Python uses Sphinx for documenting modules. That's possible. I mean, we have a prototype of a plugin for Sphinx that takes in normal Sphinx documentation and produces documentation for Judicious. So that works, and we have that for some of our libraries that we use for teaching. But the ones that you have seen for this Python standard library, those are manually written, because it's not possible to extract them otherwise.
Wonderful work. Anything that can help kids get started and form a mental model is beautiful. I was thinking, like, did you maybe look into this, like Copilot these days? If you're trying to use a function, it can pull like different sorts of examples that people have before used from GitHub. Like, is there any way you thought of like pulling examples using like through GitHub search API or something, and making it like a little bit of an automatic process, maybe? Yeah.
That could definitely be interesting. I mean, we haven't looked into generating examples, but it's indeed on our agenda, and that could be indeed a source. Although, I mean, these LLMs or Copilot related stuff are great for generating like thousands of those examples. Here it's kind of very small examples, manually curated. Every kind of word in the description is chosen to avoid possible confusions. But I mean, it would be interesting to try and see what comes out.
Thank you for the talk. I like this idea a lot. It's similar to what Racket does with the student languages, where you have scaffolding. One suggestion maybe is one of the biggest challenges students has is fixing errors, fixing bugs. So how would you feel about adding a feature or a button that says, oh, look, here are some common mistakes, and here are some possible solutions to solve that problem?
But would you imagine this at the level of, because here we're just documenting, say, one function at a time, so you're imagining issues with one specific function, for example. Okay, we haven't thought about that, but that could be possibly interesting, although I believe that the harder to fix errors typically tend to surface when the programs become a little bit bigger, and it's like more maybe on the composition of functions or on the overall logic of a couple of lines or so, and not that much at one specific function. But there, I mean, students surprise us with the confusions they can have, so it might be interesting to see what can be done.
Great. So one talk for me, and then I think we'll move on to the next talk. So one of the big ideas in this project is gradualness, and of course one of the kind of motivations for gradualness is by the end of that process to kind of have them be ready for the full version of that, in this case the professional documentation. Could you help give a sense of what gaps, if any, kind of exist between what they're using at the end of the Judicious pipeline, so to speak, versus in kind of what's out there in Python?
Yeah.
References?
I guess the main gap that remains is this is focused on let's say the functional subset of Python, so this is functional constants. And even in introductory programming with Python, it's very common to use methods. like the calling instance methods in string, and that's not at all handled in Judicious, and that would probably need to be addressed somehow to bridge the gap.
Great. Yep. Thank you very much. We can give another round of applause and.